Welcome back to Calculus 1. I'm Dr. Jeff Groh. We're going to continue our discussion of limits, but first I'd like to review a few of the concepts that we had last time. Recall that the definition of limit is as follows. By the limit as x goes to a of f of x equals L, we mean given epsilon greater than 0, we usually think of epsilon as a small number. It's a measure of closeness in the range. There exists a delta greater than 0. Delta 2 is thought of as a small number. It measures closeness in the domain. Such that if the distance between x and a is less than delta but greater than 0, the greater than 0 part implies that x is not equal to a. So we're ignoring what happens to the function at a. Then the distance between f of x and the limiting value L is smaller than epsilon. Here you can see that if we are close in the domain, then we are close to the limiting value in the range. Just for a lark, I'd like to show you some mathematical notation by which we can express the notion of limit without words. An upside down capital A is one of two logical quantifiers. It stands for the phrase for all. The second logical quantifier is a backwards capital E and stands for there exists. Also, a kind of stylized backwards epsilon with a tilde-shaped middle cross member is such that a double arrow to the right represents implies. If we have A implies B, we sometimes say if A, then B. Given all of this notation, we can describe what we mean by the limit as x goes to A of f of x equals L as follows. For all epsilon greater than 0, there exists delta greater than 0, such that 0 less than absolute value of x minus a is less than delta implies the absolute value of f of x minus L is less than epsilon. Okay, so we're not going to be doing anything more with this notation. I just thought you'd like to see it. We have a universal mathematical language that can be understood across all cultures throughout the whole world. I wanted to do one more example where we apply the definition of limit to prove that a certain limiting value. Let's prove the limit as x goes to 2 of 3x plus 5 equals 11. You can see that this is a polynomial, and so polynomials have limits that can be evaluated by simple function evaluation. You can plug the 2 in. 3 times 2 is 6 plus 5 is 11. So this is true, but let's use our epsilon delta approach. I'll show you how to find delta, which is a function of epsilon in the case of a linear function like this. So here's how our proof goes. Let epsilon greater than 0 be given. This epsilon is arbitrary. Any epsilon you choose as long as it's positive. We'll work this problem backwards we'll state first what it is that we want to conclude and try to figure out what it takes to construct this delta. We want our epsilon to be greater than the function 3x plus 5 minus 11, but we can simplify what is inside of the absolute value. This is going to be 3x plus 5 minus 11 is minus 6. And we can rewrite this as 3 times x minus 2 inside of the absolute value. The 3 can come out of the absolute value. Positive factors can come out of absolute values. We need some measure of closeness in the domain. That will be our delta. We now have this x minus 2, the distance between x and 2 in the domain, but it's multiplied by this 3. So what we're doing implies both ways x minus 2 is less than epsilon over 3. Now, the distance between x and 2 in the domain was supposed to be delta. We can see that delta has to be epsilon divided by 3. So we're going to set delta to be epsilon divided by 3. It follows immediately then, oh, by the way, a triangle of 3 dots means therefore. Therefore, if 0 is less than the absolute value of x minus 2 is less than delta, which is now equal to epsilon divided by 3, then the absolute value of the quantity 3x plus 5 minus 11 will be smaller than epsilon. And that demonstrates that this limit is true. I'd like to mention some theorems that I don't intend to prove. Not every theorem we state in this course will be proved. Some of these theorems are left for a course later on in the mathematics curriculum, in particular in a course called Real Analysis. Analysis is a branch of mathematics concerned with limits and their applications. Real analysis deals with limit concepts applied to real valued functions of real variables. You can see that complex analysis then applies to limiting concepts applied to complex valued functions of complex variables. An interesting theory in its own right. Calculus is a subset of analysis. The theorem goes like this. If A is in the domain of some trig function, trig might be sine, cosine, tangent, secant, cosecant, cotangent. Then the limit as x goes to a of this trig function at x will be equal to the trig function evaluated at a. In other words, you can calculate limits for trig functions by simple function evaluation, provided the point that you're tending towards is in the domain. So for example, if I'm taking the limit as x goes to pi over 6 of the sine of x, what I get is the sine of pi over 6, or 1/2. The same is true for logarithms and exponential functions. For the natural exponential function, you just substitute. That's true in general for exponential functions to any base. B in this case is supposed to be greater than 0 and not equal to 1. If b equals 1, It's a constant function and not really an exponential function. B has to be positive because if B is negative, you start to end up having complex valued expressions. So for example, if B was -1 and x was 1/2, we would have the principal square root of -1, namely the imaginary unit I. So in this course, we'll assume these bases for exponential functions are positive real numbers, not negatives, not 0, not 1. In addition, we have the limit as x goes to a of log base b of x is log base b of a. Again, b greater than 0, b not 1, and a greater than 0. The domain of any logarithm function is only on the positive real numbers. There's an important theorem that you need to be aware of called the Squeeze Theorem. Some people call this the pinching theorem, and it goes like this. If h of x is less than or equal to f of x, is less than or equal to g of x, for all x in an open interval containing a, the point x equals a, and if the limit as x goes to a of h of x equals L, and that's the same thing as the limit as x goes to a of g of x, so that the limits on the left and on the right are the same. The picture being like this. Suppose g is up here, and h is here. They have the same limit at a. And suppose that f wanders around inside. Then we may deduce that the limit as x goes to a of f of x must also be L. It gets squeezed in between here, in between h and g. It's pinched right there in the middle, so it has to have the same limit. We're going to apply the Squeeze Theorem to prove an important limit that you need to memorize. It goes like this. We're going to prove that the limit as x goes to 0 of sine of x divided by x is 1. Now, we talked about this before, and we showed if your calculator's in radian mode and x is very close to 0, then sine x divided by x tends towards 1. As you go towards 0, of course, the ratio is undefined at 0. But the closer you get to 0 in the domain, the closer those y values tend towards 1. We saw this intuitively before. Today, we're going to prove it. Let's begin by supposing that x is greater than 0, greater than or equal to 0. We'll deal with the negative case later. We'll draw a picture of arc of a circle. We'll suppose that the measure of the angle coming from the positive x-axis to this ray is equal to x. we're going to deal with a sector of a circle and a right triangle and another right triangle. Now you can see from the image, because this small triangle is a subset of the sector of the circle, that its area will be less than area of the small triangle will be less than or equal to the area of the sector, and that will be less than or equal to the area of the large triangle. Let's see what that means in particular. I'm going to assume that this piece of circle has radius 1. So the length of the hypotenuse of this right triangle is 1. The angle in the center here is x. The area of a triangle is 1/2 base times height. So we need to figure out the length of the base and the height. So if we call the base b and the height h, note that h divided by 1 is opposite over hypotenuse for the angle x. It must in fact be sine of x. Also, base divided by 1 is cosine of x. It is adjacent over hypotenuse. It follows then that the area of the small triangle is 1/2 base times height, 1/2 cosine of x times sine of x. Now, what is the area for the sector of the circle? Do you remember the formula for the area of a sector of a circle? It goes like this. If you have a sector with central angle theta and radius r, the area has the following relation. The area divided by the area of the entire disk, which is pi r squared, will be in the same proportion as the central angle theta to the angle all the way around, which is 2 pi. If you cancel pi from both sides and multiply the r squared over, you get the area is 1/2 theta r squared. It follows then that for us, the area of the sector is 1/2, the angle theta is x, and r is 1, so r squared is 1. The area of the sector is 1/2 x. Now, what about the area of the large triangle? Let's label its height as capital H. The area of the large triangle will be 1/2 the base. The base of the large triangle is 1. It's all the way out to the edge of the circle. And the height is going to be big H. Well, how do you figure out big H? Here's how. H divided by 1 is opposite over adjacent for the angle x. Opposite over adjacent is tangent. So we have 1/2 the tangent of the angle x. Now, let's make sense of all of this. We know that the area of the sector is less than or equal to the area of the large triangle. What does that mean? It means 1/2 x is less than or equal to 1/2 tangent x. I'm going to use the ratio identity. Tangent of x is sine of x divided by cosine of x. You can multiply both sides of this inequality by 2. We're going to multiply also by cosine x. Remember, whether cosine remember, we're choosing small values of x, and because x is being sent to 0. So we can choose x to be within some very small range. Cosine is positive in both the first and the fourth quadrants, so if you keep x small enough, this cosine will be positive, and we can multiply it over without worrying about changing the direction of the inequality. We'll have x cosine of x is less than or equal to the sine of x. And also, we're going to divide both sides by x, keeping in mind that we specifically have assumed that x is positive for now. So dividing by x will not change the direction of the inequality. We'll have the cosine of x is less than or equal to the sine of x over x. You can see this is the function we're going to take the limit of. The limit as x goes to 0, sine x over x. It is bounded below by the function h of x, which is cosine of x. We just need to have something that bounds on the other side. We'll put this in a little bucket and keep it there for later. We're going to work on this other part of the inequality. The area of the small triangle is less than or equal to the area of the sector. That implies 1/2 cosine of x sine of x is less than or equal to 1/2 x. Again, you can multiply both sides by 2 and cancel off the 1/2. We also intend to divide both sides by x. All that's left on the right-hand side now is 1. You can see that we have this sine x over x that we would like to isolate. Using the same argument as before, we can divide both sides by cosine of x, and we'll have sine of x over x is less than or equal to 1 over cosine of x. We'll put that in a little bucket. Now compare these inequalities. You can see now that we have a chain of inequalities. You can see then that by the Squeeze Theorem, we have at least the following: the limit as x goes to 0 from the right. We did, after all, assume that x was positive. Of cosine x is the cosine of 0, which is 1. The limit as x goes to 0 from the right of 1 over cosine of x. Again, cosine of 0 is 1. You get the same limit on the left and the right, and therefore, in the limit as x goes to 0 from the right, sine x over x is 1. We only need to prove that you get the same limit as you go to 0 from the left. Let me give you some prototypical examples. The function x squared is even. Why? You can see that the exponent here is even. But the salient point is that if you replace x by negative x, what does the square do to the minus? The square gives you 2 factors of minus, which just gives you x squared. And that returns the original function. Negatives disappear from even functions. that has a certain implication in terms of the symmetry of the graph. For an even function, whatever happens at x, at negative x, you must get the same thing. That gives you perfect symmetry around that y-axis. As another example, f of x equals x cubed is odd. What does odd mean? Does odd mean does inappropriate things in social settings? No. This power is an odd number. Check out what happens to the function when we replace x by negative x. You get negative x cubed. And if you have a cube on this negative, that gives you 3 negatives. 3 negatives leaves a negative. And so you get the negative of the original function. What are the implications in terms of the graph? Whatever happens at x, at negative x, you get the opposite. We'll make the following definitions. A function f is odd if f of negative x equals negative f of x. It is even if f of negative x equals f of x. So for odd functions, negatives pull out. For even functions, negatives disappear. You might recall sine is odd. Cosine is even. And you can see this in their graphs. The sine function goes like this. Whatever happens at x, you get the opposite at negative x. Sine is odd. And for cosine, whatever happens at x, you get the same thing at negative x. Cosine's even. Now, back to our proof. We're dealing with the function f of x equals sine of x over x, and I claimed that this function is even. We can prove this by substituting minus x for x everywhere in the original function. Now on the sine function, negatives pull out because sine is odd. The negatives cancel off. Our function sine of x over x is even. The negatives disappear. So that means it's symmetric about the y-axis. Whatever happens at x, you get the same thing at minus x. So in the limit as x goes to 0 from the right, you'll get the same thing in the limit as x goes to 0 from the left. We finally conclude that the limit as x goes to 0, sine x over x is 1. I'll conclude the proof with a double hash mark. This is one way that professors sometimes indicate that the proof has come to an end. There are other ways that professors indicate that a proof is over. One way is with the Cal1Mod1Lect3 finality symbol. A lot of professors will use the Cal1Mod1Lect3 finality symbol. Others will use the abbreviation QED, which stands for the Latin phrase quod erat demonstrandum. And that means which was to be shown. That would be appropriate here. We were trying to prove that the limit as x goes to 0 of sine x over x is 1, and we did, and therefore QED. Now that we've proved that sine x over x tends to 1 as x tends to 0, we can prove more easily some other limits. Let's look at the limit as x goes to 0 of 1 minus cosine x over x. What does this go to? And I want you to memorize the answer to this after we've proved it. What you can do is you can multiply both numerator and denominator by the conjugate of the numerator. In the denominator, you'll just have x times 1 plus cosine x. In the numerator, you'll end up with a kind of difference of squares sort of product. You'll get 1. You'll have a plus cosine and a minus cosine when you multiply the outers and the inners. When you multiply the last, you get minus cosine squared x. Do you recognize this 1 minus cosine squared x as an identity? It comes from that identity cosine squared x plus sine squared x equals 1, called the Pythagorean identity, because this is an immediate consequence of the Pythagorean theorem. If you move the cosine squared over, you can see that sine squared x is 1 minus cosine squared x. We have then the limit as x goes to 0, sine squared x over x times 1 plus cosine x. I want you to model what I'm doing here. Each new line begins with equals. I'm carrying the limit forward. Don't get cheap with me. Don't leave stuff off. When you leave stuff off, two things can happen. One, you're making false statements. It's no longer equal. And second, you could forget to evaluate the limit in the end. I see students doing this all the time. Be careful with your notation. Math professors usually frown upon their students making false statements. Now I'm going to separate out what remains in little pieces. One piece is going to be sine x over x. The rest will be sine x over 1 plus cosine x. Remember, you can take the limits of these factors separately provided both limits exist. The limit of this first factor we just spent a long time proving. We worked very hard to get this result, and you need to remember it, has a limit of 1. On the second part, we have the ratio of two functions, and you can evaluate those limits separately, provided the limit in the denominator is not 0. When we take the limit in the denominator, we get 1 plus cosine of 0, which is 1. So the denominator tends to 2. But what does the numerator tend to? Well, sine goes to 0 as x goes to 0. So this whole thing goes to 0 divided by 2, or 0. That means this limit tends to 1 times 0, and that's just 0. Therefore, and this is the limit you need to memorize, the limit as x goes to 0 of 1 minus cosine x over x is 0. You can see that if you just plugged x equals 0 in, cosine of 0 is 1, 1 minus 1 is 0. The bottom goes to 0 too, 0 divided by 0. What does 0 divided by 0 mean in the context of limits? More work. In this case, all of this extra work tells us that the limit ends up being 0. We've given you two limits to memorize. In the limit as x goes to 0, sine x over x is 1. In the limit as x goes to 0, 1 minus cosine over x is 0. We're going to need these in the theory later on. Let's take the limit as x goes to 0 of the tangent of x divided by x. We can rewrite this as the limit as x goes to 0 of 1 over x times tangent, but tangent can be expressed as sine x divided by cosine x. We can rewrite this expression as sine x over x times 1 over the cosine of x. Now, sine x over x goes to 1 by a lot of hard work. Cosine of 0 is 1, so the second fraction also goes to 1. And hence, tangent x over x goes to 1 as x goes to 0. So, for example, what happens in the limit as x goes to 0 of the sine of 4x divided by x? You need to be a little careful about this one. 4x is going to 0 at a different rate than just x. So here's how we can approach this one. I want the argument of the sine function to go to 0 as the same rate as the denominator. So I'm going to write 4x. I get what I want. I just have to pay for it. I have to cancel that 4 in order to maintain equality. You can see now that as 4x goes to 0, x will also go to 0. Let's replace 4x with y. We'll have the following. The limit as y goes to 0 of 4 times the sine of y divided by y. Well, sine of y over y must tend to 1. So the answer is 4. You need to know how to do this. You might also explore this on your graphing calculator. Punch in numbers close to 0 and see if you don't get something close to 4. Make sure your calculator is in radian mode. I want to look at the limit as x goes to 0. Let's do tangent of alpha x divided by beta x. I like to throw in a Greek letter now and then, just because students freak out when they see them. But I want to break them of that. I want to teach students to use and abuse these Greek letters with just like they use and abuse every other letter in the Roman alphabet that we use. Now, on this particular problem, we need to get the argument of tangent to go to 0 at the same rate as the denominator. I don't want beta in the denominator. I want alpha in the denominator. I want to have tangent of alpha x over alpha x. But I have to pay for that by putting an alpha here, so the alpha cancels and I end up with beta x. Now, the rest of this goes to 1, as we've seen, so the answer is alpha over beta. I'm not done trying to freak you out. Suppose we have the limit as x goes to 0 of the sine of psi x divided by zeta x. I know, they both look like squiggles. In this case, I'm trying to teach you meticulous attention to detail. This is the lowercase and the uppercase of the Greek letter xi, or xi, sometimes pronounced xi or xi. This is the lowercase and this is the uppercase for the Greek letter zeta. You can see now that this will be the limit as x goes to 0 of psi over zeta, sine of psi x over psi x. The second factor goes to 1, and so the answer is psi over zeta. There's one more limit you need to know about today. We're going to take the limit as x goes to 0 from the right of 1 plus x to the power of 1 divided by x. As x goes to 0 from the right, if we plug a tiny but positive number into this expression, 1 plus tiny is pretty close to 1. 1 divided by tiny. You need to know that 1 divided by tiny is huge. Try this on your calculator. Take 1 and divide by 0.00001, some really tiny number. You'll end up with something huge. So we're ending up with things that are close to 1 raised to huge powers. There's kind of a war between these two, this going to 1 and this going to infinity. As x goes to 0 from the right, these numbers are getting close to 1, but you're raising them to very high powers, which makes numbers bigger. If you raise 1 to any power, you end up with 1, but it's just a smidge bigger than 1. It's being raised to an enormous power. So we need to explore this in some depth. Let's try plugging in tiny numbers into our calculators and just see what happens. Let's try 0.1. My calculator gives me 2.593742 for 6. Well, we didn't need all of those digits. We're not nearly close enough to 0 yet. What happens when we plug in something like 1/100th, 0.01? My calculator's giving me 2.704813829. Well, at least they share the number 2. You can see that this number is going to something not very close to 1, but not like an infinite either. It's staying bounded, pretty close to 2, or somewhere between 2 and 3. Let's try even smaller numbers, closer to 0. 1/1000th. Here we go. 2.716923932. You can see now we have this 2.7 staying the same. Let's try things that are even smaller. Let's try something even closer. Let's put in 4 zeros and then a 1. My calculator is giving me 2.718268.237. .7182. These are all going to be numbers in the final answer for this limit. Let's try smaller numbers still. Instead of 4 zeros, let's put in 6. My calculator is giving me 2.718281.693. All of these numbers will be in the final limit as well. So what is this limit going to? It does go to a finite number between 2 and 3. It has a special name. It's called E. E is called Euler's number. After the Swiss mathematician Leonhard Euler, who ended up, by the way, working for the Tsarina in Russia. Euler, by the way, was the most prolific mathematician of all time. He lived in the 18th century. It's said that after he died, they searched through his papers and they kept publishing results that they found in his work. They produced, I think, several hundred papers after he died. But he produced hundreds of papers while he was still alive. In addition, he had 13 children. So I guess you could say he was prolific in more ways than one. Also, in the last 2 years of Euler's life, he was totally blind, could not see, and yet he continued his mathematical research, publishing new results, while he was totally blind. You can calculate this number by calculating e to the power of 1. My calculator gives me a decimal approximation. When I write a dot over an equal sign, I mean that I'm rounding to some decimal place accuracy. 2.718281828, and well, we'll just stop there because that's all that my calculator gives me. It turns out that Euler's number is similar to pi in that, yes, they're both irrational numbers, which means they will have a non-repeating decimal eventually. Also, e and pi are what are called transcendental numbers. All transcendental numbers are irrational, but not all irrational numbers are transcendental. Let me explain. Let me give you a definition. A number is called algebraic if it is the root of a polynomial having integer coefficients. Let me give you an example. Consider the polynomial equation x squared minus 2 equals 0. This polynomial equation has two solutions, the principal square root of 2 and minus the principal square root of 2. Both of these numbers are irrational, but they're roots of a polynomial having integer coefficients, so these are algebraic. All rational numbers are algebraic, but many irrational numbers are also algebraic. It's kind of remarkable that it's been proven that both pi and e are not algebraic. It actually took a lot of work in the 19th century to prove these two facts. Any number that is not algebraic is called transcendental. So pi and e are transcendental numbers. By the way, your textbook says calculus, early transcendentals. The idea is we introduce these transcendental numbers leading to exponential functions like e to the power of x early in the text before we can properly lay the logical, theoretical foundation for these functions. We will complete that theory in calculus 2, but we're going to use that theory early on. A lot of students who take only calculus 1 need to know about the calculus involving e to the x and natural log of x, even though they don't take calculus 2. That's why this book is called Early Transcendentals. We deal with these transcendental numbers early